from MIT. He's going to talk about spacetime symmetry-enriched SymTFT, Lieb-Schultz-Mattis anomalies, modulated symmetries, and beyond. So, Ömer Hocam, you may start if you are ready.
Yeah, thank you. Thanks a lot for inviting me. I'll be talking about some recent work that came out a week ago. Sorry for presenting with a tablet and some handwritten notes, but I thought that this way was much easier to draw some stuff. So this work is out on arXiv now for a month. It will be hopefully published soon. It's with Sal Pais, who is a PhD student at MIT, and Hotat Lam, who was a postdoc at MIT when we were working on this together. Now he's a postdoc at Stanford, and he'll move to USC as a assistant professor. So for today, I'll try to have actually a length introduction into both the SymTFT framework and also what I mean by an LSM Lieb-Schultz-Mattis anomaly in 1+1D. After that introduction, I'll have two main pedagogical examples. One will be, so the title is about space-time symmetry-enriched SymTFT. SymTFT, if you are familiar with topological order, is roughly the same as topological order. You can think of it that way. So I'll have two main examples of such topological orders. One will be a translation-enriched topological order. The other one will be time reversal-enriched topological order. And then I'll have some concluding remarks about the general framework. So the examples will be perhaps the simplest examples that this framework works for. So SymTFT is a framework that's also called symmetry topological order, also called topological holography by different people in the community. It's been a very fruitful line of research. The number of references are growing every year. So this is actually a slide that I stole from Sal that has semi-complete references up to 2025. And then I believe that in the past 7 months, there were even more papers than the last column here, last row here. So I don't claim that it's complete, but I'm just fleshing out just in case, and also to showcase that this is a growing field in both high energy physics, mathematical physics, also condensed matter physics, quantum information, all that. That's why it has also many names. Okay, what do I mean by SymTFT or Symmetry Topological Field Theory framework? It's actually a mathematical framework where, given some theory in d+1 dimension, you use the so-called topological field theory in one higher dimension to split the two parts of this theory, namely the kinematical data. I'll explain further what that means from the dynamical data of the theory. Roughly speaking, here I have a theory in d+1D with some symmetry C. This C, usually the symmetries that we are used to are group-like symmetries. They are described by a group and then they are represented unitarily. But more generally, it is some sort of fusion category. And in this talk, I'll be thinking about d equals 1, so 1+1D, and the topological field theory in one higher dimension will be 2+1D. And the goal of this framework is to express this theory in 1+1D as a 2+1D theory, a topological field theory, with certain boundary conditions. And one of the boundary conditions that I denote by boundary symmetry represents the so-called kinematical data, symmetries, and the properties of the symmetries. And the other one represents the dynamical data, so the data that is, so to say, less universal. I'll explain what that means. Just to give some nomenclature, so when C is some fusion category, this 2+1 dimensional topological field theory is sort of determined by what's called its Drinfeld center. So there's a mathematical construction given C to construct this fusion 1 category that lives in one higher dimension. And this fusion 1 category describes the topological defects of the topological field theory. It's not exactly the topological field theory, it's just the mathematical properties of the defects in this topological field theory. But in this talk, I'll use them synonymously, just as a abuse of notation. And the idea is that I have this 2+1D topological field theory that is presented in as a sandwich, what's called a sandwich construction. Since the theory is topological, actually the length of the segment actually doesn't matter at all because there's no metric dependence. Then, since this direction is topological, I can freely adjust the length, and then you can see that as the top boundary approaches the bottom boundary, this is a quasi one-dimensional system. So there's sort of a, since the bulk is a topological field theory, there's sort of a control over the quasi one-dimensionalness of the system. And the main idea is that the spectral properties of this theory in 1D, in our case 1+1D, are captured by the topological field theory in one higher dimension below some energy gap. Actually, that energy gap, to be precise, is provided by the top boundary. So top boundary is a boundary that is always topological. The word topological in this case means just gapped. So top boundary, we always choose it to be gapped. And that will encode some sort of kinematical data, namely the properties of the symmetry defect. So it chooses the symmetry. That's why it's called B symmetry. And the spectral properties of this 1+1 dimensional theory will be determined by the spectral properties of this topological order below the gap of the top boundary. So that's the correspondence, precise correspondence. Then the bottom boundary is a boundary that is not necessarily topological. It encodes everything else. It can be in principle gapped as well. It can be topological too, but it can be also gapless too. So that's why it determines the dynamical data. For instance, the excitation spectra, dispersions of excitations, etc. Whatever is not universal or not related to the symmetry. So this is a trick that allows us to remove the symmetry from everything else in the theory. Now you may ask, how do I decide what type of boundary conditions I can impose on such a bulk topological order? And at least in 2+1D, and I think in higher dimension too, higher dimensions are less understood, so there's a disclaimer there. But in 2+1D, there's a well understood formulation of all the gap boundaries of all such bulk topological field theories. Those are determined by what are called Lagrangian condensable algebras of this Drinfeld center. I'll show some very concrete example, but essentially a Lagrangian condensable algebra just means that some collection of anyons that you condense at the boundary. And then there's a selection of such anyons, namely you want to choose maximum number of anyons that are mutually bosonic, so you can condense them together. They commute they pairwise commute. And then you want the maximum number of them. So there is no remaining degrees of freedom. If you do so, you have a gapped boundary or a boundary from a topological order or topological field theory to the trivial theory vacuum here. So that's what this boundary represents. Then if I choose both the top boundary to be gapped and bottom boundary to be gapped or topological, I'm actually getting a gapped phase of matter with whatever this internal C symmetry means. Therefore, choosing different boundary conditions on the top and the bottom effectively gives me a classification of gapped phase of matter. More precisely, as I mentioned, the top boundary fixes the symmetry. So you'll see that different top boundary conditions correspond to, in principle, different symmetries. Once you fix such a top boundary, if you just iterate over all possible choices for the bottom boundary, all possible topological boundary conditions for the bottom boundary, you would get all possible gap phase of matter, which are essentially, since we are in 1+1D, which are essentially SPT phases or some spontaneous symmetry breaking patterns or some combination of them of this C symmetry, global C symmetry. And I emphasize that it is internal symmetry in this case. Then what does changing the top boundary means? Changing top boundary means that you are changing the symmetry, which effectively means something like discrete gauging. What do I mean by that? It will also be a little bit more clear with a concrete example, but starting with a C symmetry, there are certain topological manipulations you can do actually in 1D as well. That gives you another theory with a dual symmetry, which I denote by C check. And in this topological SymTFT framework, getting such a dual symmetry is the same as choosing a different top boundary condition, B check. Actually, there is a prescription to match these. So essentially, top boundary chooses different symmetries, and you can think of it as changing the top boundary as getting different dualities that are related by what's called a discrete gauging, some sort of gauging-like map. Okay, now we will focus on actually the simplest case where C is a finite, potentially anomalous abelian G symmetry. So in that case, actually, this fusion category is what's called a vec G. It is the G-graded category of vector spaces with a subscript omega. Omega here signifies the anomaly, which takes values in this third cohomology group. So it's just a way of writing the most general abelian finite G symmetry with potential anomaly. If C is such that, if C is restricted to be such, then the 2+1D topological field theory is known to be what's called the twisted Dirac-Witten theory. It's also called the twisted G quantum double. So there's a well-known prescription to construct this bulk theory in terms of the irreducible representations and conjugates classes of this group G. So these are relatively easy to understand. Even though the symmetry is abelian, because of the potential anomaly, actually the bulk topological order is not necessarily abelian. Even though I think in all my examples it will be abelian, it's just I just wanted to warn you. Okay, let me give the potentially simplest example where I set G to be just Z2. Then the Z2 quantum double is the same as essentially the confined phase of the Z2 gauge theory. This is also typically the case if you have a group-like symmetry. The bulk topological order usually some G gauge theory with a potential twist. So the twist aspect is important. And this is what is known as the toric code. So the bulk topological order is nothing but the toric code in this case. And what is toric code? It is a two-dimensional theory living on a square lattice. Well, actually, it can be defined on arbitrary lattice, the way I defined it. But I wrote the terms for the square lattice, where there are two terms. There is one term that is this AV that acts on every vertex of the square lattice. And then it consists of four X operators. These are just Pauli X operators. And there's a plaquette term BP that acts on every plaquette, and then it consists of four Z's on the links of the plaquette. So that's just the model. And this is a model of pairwise commuting terms, so it's exactly solvable. All the properties are known. And another way of looking at it is that it's a model of constraints, essentially. Because there's a minus sign in front of these terms, the ground state space is given by all the AVs and BPs set to 1. Notice that if you square one of them, you get a +1. So their eigenvalues are +1 or -1. So the ground state subspace is determined by setting all of them to be +1. Then there are four kinds of excitations. Violations of the AV terms are called E-anyons, so they are red. Violations of these plaquette terms are excitations that are called M-anyons. And if you violate both of them at an overlapping plaquette, and there's a choice there how you define that bound state, but the bound state of them is, or the fusion of them is what's called an F-anyon. And the E and M are, they are both bosons, but they are not mutually bosonic. There's a minus sign when you exchange them. And then that makes F and F fermion, actually. Then what are the Lagrangian algebras, condensable algebras? So I only have four anyons here, and I'm trying to find the maximal set that is bosonic within themselves. And then F is already fermionic, as I mentioned. So there are only two. I can either choose E, an identity anyon. Identity anyon is nothing, essentially, no excitation. or I can choose M and the identity enyon. So the topological boundary conditions are given by either condensing E enyons or condensing M enyons. Okay, now let's make a choice. Let's try to fix the top boundary. So I choose my symmetry boundary to be E condensed. And then let's just study the consequences of that. Now in toric code, there are these logical operators that are closed loop excitations that commute with the Hamiltonian. And when the topology is, when you impose periodic boundary conditions, so there's a non-contractible cycle, there are these extended loop operators, E loop and the M loop operator, that commutes with everything in the Hamiltonian. But since I condensed E enyons on the top, actually I can take such an E loop and I can push it to the boundary and I can trivialize it. That's the meaning of condensing the E enyons. Because a boundary where E enyons are condensed means that an E enyon can be created or annihilated there without any cost. That means that actually the eigenvalue of the E line, non-contractible E line, is already fixed by the top boundary. Top boundary forces it to be +1. So this is +1. However, the eigenvalue of the M line is still undetermined because the top boundary doesn't say anything about that. It is not condensed. So M line can still take the values +1 or -1. So far, that's the only consequence of the condensation of E enyons on the top boundary. Now, what does that mean in terms of choosing the symmetry? I didn't specify the bottom yet. Since I condensed the E enyons on the top, I'm effectively choosing a Z2 symmetry because if you look at the perspective of the bottom, this M line looks like a global symmetry operator that you can push and act potentially on the bottom boundary. And the eigenvalues of this M line, plus and -1, are your global symmetry eigenvalues. And since there's only two values, actually, the corresponding category is just vec Z2 or just an ordinary Z2 symmetry. Essentially, the message I'm trying to give is that once I condense the E lines on the top, the remaining M line that is not condensed act like a Z2 symmetry, M enyon line in this construction. Below the gap of the top boundary, of course.
Can I ask something?
Yes.
So is this 1 plus E boundary condition equivalent to saying that E has Dirichlet boundary conditions because it ends on the boundary?
Yeah,
and
yeah.
M is
In
free,
the
so it's like, I can think of it like that.
In the gauge theory, one is Dirichlet, one is Neumann boundary conditions. Indeed, it depends on how you call what, but I think that's exactly how it is.
I see.
Depends on your convention, what you call charge and what you call flux. Yeah. Now let's try to choose the remaining. Let's actually compare the remaining two gap boundary conditions for the physical boundary. So I'll choose another topological boundary condition now for the bottom one. First, I'm thinking of again condensing an E enyon on the bottom. So what does this give me? Now I can have an E line, E enyon line that starts here because remember that E enyon is condensed on the top, so an E line can end there. And then now an E line can also end here. So this means that there is such a tunneling event. This is really this operator implements a tunneling of E enyon from top to the bottom. But this operator, what does it do? It commutes with the Hamiltonian, but it anti-commutes with the M line because there's a relative minus sign between the M and the E lines. Therefore, it switches the M eigenvalue. That means that there will be two degenerate ground states because both of these line operators commute with the Hamiltonian, but they anti-commute. Another way of interpreting this is that this E enyon now acts as the charged operator, local charged operator under the M line. There are several observations. One is that since I condense E on the top and E on the bottom, I can actually not move the M line at all. It commutes with the Hamiltonian, but I cannot trivialize it. On the other hand, I can effectively, from the perspective of the physical boundary, it feels like this charged operator E takes a non-vanishing expectation value. And then this gives a nice interpretation about this twofold ground state degeneracy. We now interpret this as the Z2 SSB phase, something like ferromagnetic phase of the global Z2 symmetry that is set by the top boundary. So the E anyons act like charged operators. Now, conversely, what I can do is that I can choose the opposite boundary condition for the bottom. I can condense the M boundary here. What does this mean now is that there is no tunneling event that can take place. So actually, I mean, you can really write down the stabilizer and find its ground state subspace, and you'll find that the ground state degeneracy is just 1. And the interpretation for this is that this is the paramagnetic phase of the Z2 symmetric, a Z2 symmetric Hamiltonian. It's the Z2 preserved phase. And one nice observation to make is that since I condense M anyons here, I can actually take my M line, push it to the physical boundary, and then let it disappear because M anyons are condensed there. So that really feels like a symmetric non-degenerate ground state where a disorder operator takes a non-zero expectation value. Just to remind that disorder operator in Ising model, for instance, would be some product of sigma x's, some finite product, and that would get a non-zero expectation value in the paramagnetic phase. So the symmetry operator gets a non-zero expectation value. So the ground state must be symmetric. So this is a Z2 symmetric phase. All right, so that is essentially how you get the two gapped phases, for instance, of the transfer field Ising model using the toric code as a 2+1 dimensional bulk topological field theory. Now you can do something else. You can just switch the labels E and M. You can start with the M line on the top, and everything follows exactly the same, except now what was Z2 preserved phase became Z2 SSB phase. And what was the SSB phase became preserved phase. And the ground state degeneracy went from 2 to 1 and 1 to 2. And those that are familiar with the transfer field Ising model would realize that actually the EM exchange symmetry of the toric code, or EM exchange duality sometimes called, is acting like Kramer-Vanier's duality for the transfer field Ising model, or effectively gauging the Z2 symmetry. So that's what I was trying to tell you when I said discrete gauging. So choosing an M boundary here as opposed to E boundary effectively implements a discrete gauging for the physical theory. And instead of the M anyon, now E anyon X. And the global symmetry in principle is now rep Z2, but rep Z2 is the same as vex Z2, which is the same as Z2. So in this case, the symmetry doesn't change, it's just Z2. But in more complicated cases, changing the top boundary can also change the symmetry. It's not guaranteed that the symmetry will remain the same. Okay, now I'll change the topic completely. This was my very short, quick crash course on SymTFT framework. Does anybody have any questions? Essentially, the main points I wanted to highlight is that you can get gapped Hamiltonians and you can get dualities out of this SymTFT framework without writing down a Hamiltonian, just using the properties of the bulk topological order.
I have one question. So if we insert some Kramer-Vannier duality defects in this blue region, then shouldn't we have some uplift of the symmetry to a Tambara-Magami category?
You are thinking something else. You are thinking that, so this topological order, actually the topological order itself does not have the symmetry, but it can have the symmetry. In our lattice model, the coefficient of the star term and the plaquette term was the same. So there was an exact symmetry of E and M exchange. They have the same excitation energy. I'm just saying that I can have a global operator, a 2+1, a two-dimensional operator that I can act on everywhere that changes the labels of M and E. That's all I am saying. And then effectively that implements, from the perspective of the physical boundary, it implements what's called a Kramer-Vanier's duality. Now, what you are referring to is actually taking this two-dimensional symmetry of the bulk topological field theory and gauge it. If you gauge it, you get a new topological order. And that topological order will be Z2, yeah. It will describe the Z2 Tambara Megami on the boundary. The topological order will be this Ising plus Ising star or Ising bar topological order. So that's one way of getting new topological order. So you start with a topological order 1, and then you gauge some global symmetry, and you get a larger or smaller, actually depends on what kind of symmetry you are gauging. You get another topological order. And that would describe another symmetry, actually. It would describe exactly a fusion category symmetry. That's not a group like. It would describe this C2 Tambara Megami symmetry. Okay. If there's no other question, I'll actually return back to 1+1D and sort of give another crash course on what I mean by Lieb-Schultz-Mattis anomaly or Lieb-Schultz-Mattis theorem. So I start with a Hamiltonian. This is this XYZ model where XYZ are again Pauli operators coming with coefficients that are not necessarily equal, delta XYZ. Such that all the deltas are larger than 0. So this is an antiferromagnetic model. And this model has, for any value of the delta, has two kinds of symmetries. The first symmetry is the Z2X times Z2Z spin flip symmetry that is implemented by just product of x's and product of z's. You can very quickly verify that these are symmetries. If you act with product of x's, each y and each z gets a minus sign, but there are always two y's and two z's, so it comes with the Hamiltonian, and the same for the product of z's. And product of y's is also a symmetry, but it's the diagonal element. It is the product of that times product of that. And there's I have L sites, and there's a ZL translation symmetry. I didn't write the operator for it, but its action is that it takes any operator localized at site J to the site J+1. It just moves things. And the L power takes you back, so I impose periodic boundary conditions, so it's a ZL translation symmetry. Now, if you look at the phase diagram of this model, it's not very hard to construct it. I choose some parameter space such that sort of the directions where you go to the tips are when the delta x, delta y, delta z are the largest. So here you can imagine this as the point where delta y and delta z are 0 and delta x is non-zero. And similarly, this point represents delta y non-zero and the other two being 0. In such a parameter space, one notices that there are 3 gapped phases. So whenever one of the deltas is larger than the others, it dominates when it is sufficiently large, and then it opens a gap, and there's a twofold ground state degeneracy in each of these phases. But there are different symmetries that are broken. For instance, when delta x is very large, x flip symmetry, spin flip symmetry along x-axis is unbroken, and the phase is nil x phase. Because actually in this very corner, when both delta y and delta z are 0, the model is classical. There are really 2 ground states where it is anti-aligned spins in x direction. And similarly in y direction and z direction. So these are nil y phase and nil z phase. And these are the subgroups that are preserved. I just wrote down the subgroups of spin flip symmetry that is preserved in this phase diagram. And as a matter of fact, translation is always broken, but I could have had written another model. I could just change the sign of the deltas, all the deltas, and make them ferromagnetic, then the translation would be preserved. The important observation about this phase diagram is that there is no gapped non-degenerate ground state in the parameter space. And all gapped phases are SSBs, spontaneous symmetry breaking phases. Everything is twofold degenerate. And these lines, by the way, are all critical points described by C equals 1 CFD. Okay, then you may say, so what? Why is there, I mean, why should I care about it? At the end of the day, it's just some parameter space with 3 parameters. But actually, this is not a coincidence that there is no non-degenerate gap ground state because there is an underlying so-called LSM anomaly. There's a theorem, the original Lieb-Schultz-Mattis theorem comes from 1961. It was for another model with slightly different symmetries. It was for a model with continuous symmetries, but this is it's one of the latest incarnation with Z2 times Z2 internal symmetry, proved by Ogata and Tasaki, I think in 2019. or 18, something like that. And then what they prove is that if you have a spin chain with ZL translation and Z2 times Z2 internal symmetry, whatever symmetry that is, such a spin chain cannot have a non-degenerate and gapped ground state if the local representation of this internal symmetry on each repeat unit cell is a non-trivial projective representation. So, okay, there's a little bit to unpack. What do we mean by a local representation on each repeat unit cell? There's a hidden assumption that the symmetry operators are formed by product of some local representations. And if you recall, that's actually the case for us. Our symmetry operators are indeed product of some local operators at every repeat unit cell. And we have translation symmetry, so they are uniformly the same symmetry at every site. And in our case, the local projective representation at each unit cell is then a single X or single Z. And what does a projective representation mean? If you look at the algebra between these local operators, you would find that they anti-commute. This is no big secret. But the important thing is that you cannot absorb this minus sign by any redefinition of phases, actually. This minus sign you cannot get rid of. It's a spin 1/2 representation, if you wish. It's coming from there. And more generally, given some lattice system size L, the global symmetry operators also can anti-commute when there are odd number of sites. That just means that when there are odd number of sites, the total spin is some half-odd integer. Therefore, these operators anti-commute. And whenever that happens, actually, globally, you have some degeneracy. But actually, what is the non-trivial statement here is that even when L is even, so the global symmetry operators commute with each other, the local anti-commutativity prevents you to have a non-degenerate gap ground state. And the interpretation that I want to give this theorem, the result of this theorem, it's just a theorem, is that there's a mixed anomaly between this internal symmetry and this translation symmetry. Because what theorem allows us is that I cannot have both translation invariant and internal symmetric non-degenerate gap ground state, but I can have a gapped ground state that breaks translation, but not the internal symmetry, or internal symmetry and not translation, and vice versa. At least that's within the realms of the within the possibilities of the theorem. But I cannot satisfy all these together. So I cannot have all the symmetries at the same time with a gap ground state, non-degenerate gap ground state. So this I want to call LSM anomaly because it reminds us an anomalous symmetry. Usually what's called a Tooth anomaly is it comes with such a no-go theorem where you cannot have a non-degenerate gapped trivial ground state when you have such a Tooth anomaly. Okay. So that's what I mean by LSM anomaly in 1 plus 1D, but I'll do a little bit more for this LSM anomaly. Now, mixed anomaly means something. It is understood in terms of, it is understood well for internal symmetries. But now we have a mixed anomaly between some internal symmetry and translation symmetry. So I just want to test if it really is, if it really feels like a mixed anomaly or not. So one consequence of having mixed anomaly is that if you gauge a non-anomalous subgroup, you should get a group extension. What do I mean by that? So these are the very typical examples. For instance, if we had two Z2 symmetries, Z2A and Z2B symmetries with some mixed anomaly, once you gauge one of the Z2, so mixed anomaly means that the Z2A or Z2B are not anomalous themselves, but together there's an anomaly. When you gauge the Z2A symmetry, you get a dual symmetry that is Z4B. So you see Z2B is extended to Z4. This is a non-trivial group extension. Another such example is what's called a type 3 anomaly for 3 Z2 symmetries, ABC. And if you gauge one of the Z2 symmetries, you get actually a little bit more complicated group, but it's just non-abelian group. The simplest non-abelian, one of the simplest non-abelian groups is just the group D8, dihedral group of order 8. So that's another group extension of Z2 times Z2 by a Z2. So to motivate the name LSM anomaly, let's gauge a non-anomalous Z2 symmetry, namely Z2Z symmetry. I just choose that out of the all spin flip symmetries.
Can I
Okay,
add
so
something before this?
yeah.
So are there cases where gauging the Z2 asymmetry, let's say, gives a higher group instead of a group extension?
This is all in 1 plus 1D. If you just take an ordinary Zn symmetry in 2 plus 1D, gauging that Zn symmetry would give you a Zn 1 form symmetry. Usually there is that hierarchy. So if you gauge a 0 form symmetry in 2 plus 1D, you get a 1 form symmetry. If you gauge a 0 form symmetry in 3 plus 1D, you get a 2 form symmetry, and so on. So.
Yeah, but I didn't mean like higher form symmetries. I mean higher group symmetries. Because when you have a mixed anomaly between two symmetries and you try to gauge one.
Do you want to start with only 0 form symmetries? I can imagine like...
Because we are in 2 dimensions, so 1 form symmetry is not that interesting.
Okay, I don't know one example on top of my head, but I can imagine that if you have some mixture of higher form symmetries with some 0 form, 1 form symmetries with some mixed anomaly, gauging should give something interesting. Yeah. Okay. So let me describe this gauging Z2 symmetry. So I was talking about gauging a lot since the beginning of this talk. So here is a concrete example. So to me, gauging has these following steps. I want to gauge a Z2 symmetry, so I introduce some new degrees of freedom. I introduce them at the links. So J plus 1/2 means that a link between J and J plus 1. And then I introduce some Z2 degrees of freedom. So these are just Pauli matrices again, because I want to gauge a Z2 symmetry. Now I enlarge my Hilbert space by introducing all these additional degrees of freedom. I don't know what to do with them in principle. Then in my second step, I impose a Gauss constraint. And the Gauss constraint is such that I take my symmetry operator and sandwich it between one of the Z2 degrees of freedom. The way to think about it is that these take the role of an electric field. So actually this product is like divergence of E. And then this takes the role of a charge. So setting the Gauss law equals to 1 is similar to exactly the Gauss law. So that's why it's called Gauss constraint. But importantly, I'll look at the subspace where all the GJ operators are 1. They are all pairwise commuting by construction. So I can set them to be 1. That's not always possible. For instance, in non-abelian gauge theories, you cannot set them to be 1 simultaneously. I mean, it's not trivial. At least you need to project into some singlet subspace. And on the other hand, also, product of all the Gauss operators gives me the global symmetry operator. So in the subspace where all the Gauss operators are set to 1, my global symmetry will be trivialized. So it will be gone. It will be a gauge symmetry. It will not be a symmetry anymore. It will be a constraint. Then the third option, third step is that now, since I impose a Gauss constraint and I really want to set G to be 1, I need to do this minimal coupling scheme to make everything gauge invariant. What do I mean by that? In my Hamiltonian, I had this xj plus 1 term, which do not commute with all the Gauss laws, Gauss operators. So I add a sigma x in between. Then I make sure that it commutes with all the GJs, because if I act with a GJ here, there's a minus sign coming from here, but there's another minus sign coming from here. And then the role of the sigma x is the gauge field. Really, it's the same process as putting a gauge field when you make a theory gauge invariant. And similarly for the y's, and then z's are already gauge invariant, so I don't do anything. Something interesting happens here, actually, that's not standard, and that's actually where I'm trying to get to. My global symmetry operator, the other global symmetry operator that is not gauged, is also not gauge invariant, because the product of x's don't commute with the Gauss law. So I need to do something with it. One way of doing is that, by the way, now I set the number of sites to be 2L. There's a reason for that. If the total number of sites is odd, I really cannot gauge this symmetry. The only way I can gauge it is if the total number of sites is even, so that the global symmetry operators commute. Now with number of sites set to be even, I actually pair the x's because I can just pair them up. Each x will have another x, so I pair the x's on odd sides with the x's on even sides next to it, and put a sigma x in between. then now it's gauge invariant. So this is the gauge invariant form of this symmetry operator. So not only Hamiltonian got modified, but also the global symmetry operator got modified. And actually, I successfully gauged the symmetry. At this point, you can stop. It is just that this Hamiltonian with this symmetry subject to the condition that Gj is 1 is enough to gauge the symmetry. But we can do a little bit more than this. This is not always possible either, but gauging just a Z2 symmetry, this is possible. We can have a simpler form for this Hamiltonian. That is by a procedure called gauge fixing. But in essence, it's just a unitary transformation. There's a unitary shift where you shift this product such that each Zj is shifted to by sigma z's next to it to get a Zj. So this is really a unitary. Arrow just means a unitary rotation, a unitary transformation. Then this pair, sigma x sandwich between x's, goes to just sigma x. And y sigma xy goes to 2z's. And then this pair of 3 zxz's. And the nice thing about it is that Gauss operator goes to just sigma, zj. And then I want to look at the subspace where the Gauss constraint holds. That means that I'll just set the zj's to be 1. So when I do that, I get rid of all the zj's. Gauss law is also gone. And actually in my Hamiltonian, nicely, there is nothing remains of the original degrees of freedom. It's all in terms of the gauge degrees of freedom. And there's no Gauss constraint anymore. And I also changed the notation a bit. I don't like the operators sitting on the links, so I just shifted them. So j plus 1/2 became j plus 1. It's just the relabeling. And I get this Hamiltonian. It's not very important what the Hamiltonian is. We are more interested in the symmetries. Now, as I mentioned, the Z2Z symmetry is gone because it is gauged. Now we have a dual symmetry. If you look at the form of the Hamiltonian, all the terms commute with the product of sigma x's. There are 2z's here, 2z's here, and the x commutes with itself. So there's a dual symmetry now. I gave up a Z2 symmetry, I gained a Z2 symmetry. And then I had another Z2 symmetry that was just sitting there. I made it gauge invariant and I was just following the procedure. Now it became this, because recall that when I made it gauge invariant, I paired the x's. So each pair there were 2 L terms here, and then there are L terms here. And then each of these pairs only give 1 sigma x's. So it became a symmetry where sigma x operators only act on even sides. So that's the dual image of this Z2X symmetry. Interestingly, what happens now is that if you act with translation on this, which is sigma x is on even sides, you get sigma x is on odd sides. But sigma x is on odd sides is nothing but sigma x is on even sides times all the sigma x's, essentially, because sigma x squared is 1. And this algebra describes a Z2 dipole symmetry. It's a dipole symmetry because this you can write as J1 2L sigma xjj, because whenever j is even, this, or 2j plus 1. Whenever j is odd, it will drop out. Actually, I can type it. And then this looks like a dipole moment in 1 plus 1D. So that's what's called a Z2 dipole symmetry. And if you look at the global symmetry structure, we have the translation symmetry that now has an action on the internal symmetry. So that's why there's a semi-direct product here. Actually, the D8 is contained in this full symmetry group, but it's not exactly D8. The more important thing is that there was a non-trivial group extension. So that is to further motivate the notion of LSM anomaly. Okay, so what we have learned is that there's this what's called an LSM anomaly in 1 plus 1D. The simplest example is this Z2 times, one of the simplest examples is this Z2 times Z2 symmetry. And if you gauge a non-anomalous subgroup, you get this non-trivial extension. So there's a non-trivial interplay between translation and internal symmetry. Okay. And why did I introduce all that is because, as my title dictates, I want to have SymTFT construction, but I want to supplement it with some space-time symmetry. The reason is that I try to emphasize, but SymTFT works best for internal symmetries because we want a gauge theory, some G gauge theory in the bulk. But if you have some space-time symmetry, it's not obvious, it's far from obvious that how to genuinely gauge, how to write a gauge theory for translation in 2+1D. Actually, I don't know if lattice translation can even be gauged to begin with. So that's not a well-defined notion, at least to me. So we'll do the best thing that we can do after that. What we are going to do, so that's the motivation. I want a SymTFT description that also captures the interplay between space-time symmetries and the internal symmetries. And what am I going to do is that whatever internal symmetry I have, I will gauge it. For instance, in the case of Z2 times Z2 with translation, I'll look at the Z2 times Z2 quantum double. And then the space-time symmetry, I'll make it a symmetry of the topological order. So I'll enrich the topological order by this symmetry. So that's why I call this construction space-time symmetry-enriched SymTFT description. And there will be two directions. So remember that this translation came from our physical theory in 1D. So that's the X direction. So it will be the translation in that direction. And then Y direction will still be topological. That's important. I don't do anything there. I don't do the enrichment there. Really, the enriching symmetry comes from the lower dimensional physical theory. Okay, now with that, let me construct this translation-enriched topological order. There are sort of two ways to do that. So I want to place this theory with LSM anomaly at the boundary of a two-dimensional theory, two-dimensional gauge theory. So one thing I can do is that I can take what's called a 2+1D weak SPT. This is nothing but you take one-dimensional SPTs. In this case, these are Haldane phases that are protected by an internal Z2 times Z2 symmetry. And then you take L copies of them and you stack them, construct this two-dimensional lattice. The point is that if you have the Haldane chain, the boundary realizes a projective representation of Z2 times Z2 symmetry. So the boundary of this two-dimensional model looks exactly like my boundary of LSM theorem, where LSM theorem applies. So each of these lines is a one-dimensional SPT, and then together the 2D theory has this LSM anomaly at its boundary. This is also what's called an anomaly in flow theory. So I had this LSM anomaly, and then I put a two-dimensional theory where the anomaly is matched. And once I have this theory, this is an invertible theory. It's not a topological order. It's a topological theory, but invertible. I can gauge the internal symmetry everywhere, make the bulk a gauge theory. That's one way of getting it. On the other hand, I can do the other way around. I know that the LSM is related to dipole by gauging. So I can have some sort of dipolar SPT, some SPT with a certain dipole-like symmetry and gauge that symmetry. And I'll not show it, but indeed, actually, these two give you exactly the same answer. That already suggests this duality between Z2 times Z2 symmetry with LSM anomaly and the dipole symmetry. I'll just give you the result. If you follow that, you get another, something that's very similar to the toric code. You get another model with some stabilizers that I label by AR and BR that are some sort of modified star term and modified plaquette term. And the definitions as follow: for every R, AR, for some reason that is not clear at the moment, but I hope will become clear. So if you do this gauging carefully, that's actually what you get. It's just almost the same star term, but one of the x's went from here to there. And there's a generalization of Z for Zn, which has x's all over the place, but it's a modified star term. Similarly, plaquette is in the same sense similar. So there is a Z that's moved away. But then the important question is that what's the ground state subspace and what are the logical operators? What are the line operators that were these E lines and M lines? Because At the end, I'm claiming that this is not toric, this is Z2 times Z2 topological order. And there are 4 of them. So these are closed loop operators that commute with the Hamiltonian, every term in the Hamiltonian. These are for very short loops. So you can imagine something like that. And then similarly, that's some sort of M line. And then they come in two forms. This V1 and W1 are sort of translation invariant. This is a very shorthand notation. Actually, there's some index that moved. But what I'm trying to say is that if you act with the translation in X direction, this loop operator is just shifted by one side. Nothing interesting happens to that. But V2 and the W2, they are slightly different. If you act with the translation operator on that one, you don't get the same operator shifted by one because there is a notion of evenness and oddness. For instance, look at this V2 operator. It has x's on only either even or odd links in the x direction, only one of the directions. Therefore, when I shift it by one side, I need to multiply by V1 to correct it. So the translation is a non-trivial action on these loop excitations, loop operators. They are not excitations that commute with them. So these loop operators have some non-trivial interplay with the translation, which suggests that the anyon operators that would be at the ends of the open strings will have also non-trivial interplay with translation. And that's indeed the case. Okay, this is a side remark. One thing is that actually you can also go to continuum limits and write down a field theory for this SymTFT. And it turns out that it's not a topological field theory, precisely because of this action of the translation. Instead, it is topological in the time direction and y direction, but it's not topological in the x direction, because the action that you would get depends on some background E that knows about something about the lattice. It is just dx. So this is the wedge product. So dx is the component there. And then there is this lambda, which has the units of inverse lattice spacing. So there's some UV cutoff. And then this is what's called the foliation structure. And not only coupling to E affects the properties of the anyons, it also tells something interesting happens when you try to translate the anyons. Essentially, this coupling, as I will show, tells you that the anyons needs to be permuted by the translation operator. And this is one way of writing the field theory, some sort of continuum field theory that's coupled to some background structure. I should quote a structure. It's not exactly a background field, but it's a foliation structure. It acts like a one-form field. There's a dx. And it also affects the gauge redundancy. For instance, the gauge redundancy for A is not just A plus D alpha, where alpha is some scalar, but it comes with, so it is coupled to the foliation. And because of that, in the x direction, this field theory is not strictly a topological field theory, but we are still safe because it is still SymTFT in the sense that we want. It is still topological in the compactification direction. That was why. So I can still change the length there without any problem. But the lattice spacing on the x direction is important. And actually E sort of knows about that, the lattice spacing. It roughly knows about the number of leaves in your construction, because your construction is not exactly smooth. It has some lattice spacing and there are some one-dimensional subsections, and then E knows about that. Okay, so that was a side remark to just say that this is not exactly a topological field theory, but it does the job. So
Can I
first
ask
of
something?
all, yeah.
So when we have a SymTFT that is not fully topological, how does the classification of topological boundary conditions change on the
Yeah,
symmetry boundary?
I'll come to that. I think that's subtle. I'll show you one proposal, because once I constructed this translation-enriched topological order, I'll also talk about the gap boundary conditions, and then I'll demand that the gap boundary conditions are translationally invariant. But that's our proposal. So and then that proposal gets you to some point. That's maybe one way of explaining it.
Okay, thanks.
Essentially, if you want to incorporate some sort of space-time symmetry, you want your gauge fields to know something about the underlying lattice. If your goal is to put this information about the lattice structure or the lattice space-time symmetries. And this is a Z2 times Z2 topological order because there are 4 logical operators, and you can open them up. That creates 4 kind of excitations. Because the gauge symmetry is Z2 times Z2, I'll label them E1, E2, M1, M2. For each Z2, there's an E anyon and there's an M anyon. So any excitation can be written as some product of these 4 with some coefficient A, B, C, D that are 0 or 1. And then there's a choice, what I call E anyon and what I call M anyon. We make the choice such that E1, E2, M1, M2 are identified with this product. It's just a convenient choice. There are other choices because you can relabel this stuff. And the point is that once you do this identification and this choice, the translation has an action on the anyon, so it permutes it. For instance, the E1 anyon is mapped under translation to E1, E2, and the E2 anyon is mapped to E2. And the M1 is mapped to itself as well, and M2 is mapped to M1 times M2 as well. So there's an untrivial translation action in the field theory that was determined by this coupling to the foliation field. And now it's your question. So our proposal is the following. If you look at the Z2 times Z2 topological order, there are 6 Lagrangian algebras that I wrote here. You don't need to memorize them. It's just that I wrote the action on translation on them. So out of the 6, 4 of them are closed under translation. They preserve this enriching translation symmetry. And then 2 of them are exchanged by the translation symmetry. Our proposal is such that whenever we construct a sandwich, we want to have both the top and the bottom to preserve the translation symmetry. If you don't do that, I think for translation, it's not a big issue. But once you include things like reflection or time reversal, some additional symmetries, you run into trouble if you don't impose. We'll see roughly what happens. So if you don't impose the symmetry condition on the top and the bottom boundary. So out of the 6 Lagrangian algebras, I'll only keep 4 of them because those are the translation invariant ones. The goal here is that I just keep these 4 and I'm asking, can I learn something about the LSM anomaly just by looking at these 4 and the duality? So I'll only keep those 4 of them. And let's choose, I'll not do all possibilities, I'll just do 2. Let's choose the top boundary, the symmetry boundary, to be the one where all the E anyons are condensed. So what does this mean? If you remember from the toric code, whatever is not condensed was becoming the symmetry operator. So now I condense the E anyons, which means that now the symmetry, effective Z2 times Z2 symmetry, will be generated by M1 and M2 anyon lines. These are the unspecified ones in the bulk. But importantly, translation has an action on M1 and M2. It doesn't change M1, but it takes M2 to M1 times M2. And that should remind you something. That's exactly the algebra, the action of translation on the Z2 dipole symmetry. So the claim here is that once you choose this top boundary, you are actually effectively choosing the Z2 dipole symmetry. Then I can put the other 4 on the bottom and classify the phases. And then it replicates the Z2 dipole symmetric phases where the translation is preserved exactly. So there are 4 phases. There's one phase where the Z2 dipole symmetry is completely broken. So both the M means the monopole symmetry, the uniform part. Dipole means the one that is only acting on even or odd sides. The first one is the complete symmetry breaking phase. It is 4-fold degenerate. The second one is only the dipole symmetry broken and not the monopole symmetry broken. Actually, if you don't break translation, this is one of the allowed SSB patterns. And the other 2 has unique ground states. And those are the 2 SPT phases that are protected by this dipole symmetry so there's a trivial SPT that is just a product state, and the cluster SPT is this, maybe you are familiar with this ZXZ model. that can be protected by x's on odd sides and even sides. So that's the logic. So there are two SPTs with ground state degeneracy one. Then let's choose another boundary. Oh, this was L1, and I think this is L3, sorry. What I did is that I actually did something like gauging, what I was calling gauging. If you recall changing an E and M ion, I was telling you that it is like gauging a Z2 symmetry. And then E ion is also unaffected, sorry. Yeah, E ion is also unaffected by the translation. So changing it is like, exchanging E1 and M1 is like gauging the monopole symmetry. And the monopole symmetry should give me back to LSM, and that's indeed the case. So I just have this boundary where I exchange every E with the M. So I just gauge the symmetry. And now what is not condensed is E1 and M2. And those are my symmetry operators, but those are precisely the anyons that are invariant under translation. So that's a uniform symmetry. Translation doesn't act on it. But there is an LSM anomaly. How do I see that there is an LSM anomaly? Let's put all the translation invariant Lagrangian algebras here. And the translation invariant Lagrangian algebras are all breaking one of the internal symmetries. So if you look at the SSP patterns corresponding to these Lagrangian algebras, you find that 3 of them are precisely the 3 nil phases, X, Y, Z. Only the Z2X, Z2Y, Z2Z symmetry is preserved. And the 4th one is complete symmetry breaking. That is not in the phase diagram, but you can tune some Hamiltonian that realizes that. And the other 2 Lagrangian algebras that I didn't include were breaking the translation symmetry. And actually, they would be the one that would give us SPTs that would preserve this symmetry, but they're breaking the translation. So that's the LSM anomaly, the essence of the LSM anomaly, captured by this translation-enriched Z2 times Z2 topological order. Okay, so that's my proposal and the simplest cute example where Z2 times Z2 topological order with translation captures this dipole symmetry, its LSM, corresponding LSM, anomaly, and so on. It can be generalized. I'm just not showing it for the time purpose. I already exceeded 1 hour. You can generalize this to any modulated symmetry, and the structure will be richer because translation can act many different ways on internal symmetries. Now I want to move to another interesting example where there's a time reversal enrichment of a Z2 topological order, just for completeness. And I'll again start with a 1D lattice model, but I'll be much faster. Consider the Z2 time reversal symmetry. So this superscript T just means time reversal. It means that the symmetry operator will be anti-unitary times Z2 symmetry. That's implemented by the following operators. So my Z2 operator is just product of Z's, nothing interesting. My time reversal operator is complex conjugations times this weird object. So it's somewhat complicated, but actually it doesn't do, its action is not, its action is not that that complicated. I didn't write it because it's not very important, but roughly it takes xj to xxx nearby x's and y to y, and then doesn't act on z. It does something along that line, if I recall correctly. And you can write a Hamiltonian. Actually, the xy model is invariant under that. The point is that actually these two Z2 symmetries have a mixed anomaly. One is time reversal and the other is an internal Z2. So you cannot have an undegenerate gap ground state with these symmetries. And indeed, the XY model has gapless spectrum. So that's a Hamiltonian that fits into the claim. But to see why this two Z2 symmetries are have a mixed anomaly, I can gauge the Z2 symmetry implemented by U. And the gauging map is fairly simple, but it gives me this time reversal, dual time reversal operator. Notice that if I gauge the Z2 symmetry by that is implemented by product of Z's, the terms in the exponents are not invariant, so I will need to do a minimal coupling, all the things that we had done. But if you follow it through, you get another operator, which is instead of xy, yx, it is yz, zy. It doesn't look like a big change, but actually it is. If you square this operator, you find product of x's, which is the dual symmetry actually in this representation. So your Z2 time reversal became a Z4 time reversal. And this is exactly the central extension I was talking about applied to the time reversal symmetry, Z2 time reversal symmetry. So, okay, this is 1D example with anomaly. There's a Z2 times Z2 with anomaly. There's a Z4 that is not anomalous. Now I want to have the topological order that realizes it. And I'll again give the I'll just give the result, but the way to construct it is that you start with some Z4 SPT in 2 plus 1D, Z4T SPT, sorry, and then gauge the Z2 subgroup of it. And the result is a Hamiltonian of this kind. It's actually, this is much more closer to toric code. It's essentially toric code. Now, these calligraphic X operators are not Pauli's anymore. Instead, they are Z4 clock model operators. In particular, a Z and X don't anti-commute. Instead, there's an I phase factor. So these are four-dimensional matrices. So Z, you can imagine it as 1 I minus 1 minus I. And then X is some shift operator that shifts the eigenvalue by I. Now the Hamiltonian consists of just X plus X dagger. X is not Hermitian anymore, so I need to add the Hermitian conjugate, times some plaquette operator. And the plaquette operator is exactly the plaquette operator of toric code. But now I have a global Gauss constraint, and I impose it. So the star operator is not something dynamical in the Hamiltonian, but instead it is imposed, where I impose that X square, calligraphic X square, times AR. Oh, this is a typo, sorry. Oh, I don't know. I
Hocam,
couldn't
by the
read.
way, we don't have time limitation, so you can go on
Okay. Okay, thank you.
as you wish. Yeah.
So it is local X square operator that is sandwiched by sigma x's. So this would be almost like a star operator. But in my Hamiltonian, if I try to replace XR with something, I need to replace it with square root of this. So I'm not doing it. Actually, there's a way to do it. I'm just not doing it because this representation is much better. I just gauge the X square operator. And this is a Z2 topological order. The star and the plaquette already tells you sort of that, with some global time reversal symmetry. And the time reversal symmetry is just complex conjugation time product of calligraphic x's. And the U square is X square, but product of X squares is product of all the star operators, and that's identity if you have a closed manifold. So as long as I have a closed manifold, this time reversal operator squares to identity in the constraint subspace, in the physical subspace. So it's not an operator identity, but it is an identity in the subspace where Gauss constraint holds. So that's the construction. This is the claim that this is the correct Z2 time reversal enriched Z2 topological order. Okay. Now this time reversal symmetry is interesting because it realizes a non-zero symmetry fractionalization on the E anyons. What do I mean by symmetry fractionalization? Usual law of symmetry fractionalization is the following. You have some global symmetry operator. In this case, the time reversal symmetry operator. You take a single excitation. In this case, I claim that it's the E anyon. So I have a single E excitation. And then you implement this symmetry on the patch, which I denote by sigma. And the claim is that this excitation carries fractional charge. So that's the meaning of symmetry fractionalization. So the time reversal squares to -1 on the E anyon operator. This is a very vague idea because time reversal is an anti-unitary operator. It's not clear how to restrict it to a patch and so on. But on a single anyon, it should square to -1. So let's do that in another way. To be able to do that, I'll start with the Hamiltonian and I put a single E anyon trapped at some site. One way of doing it is that you create an open string of sigma z's. If you have an open string, this is a semi-infinite string, so it goes to infinity. The end of the string should create an E anyon because it anti-commutes with the Gauss constraint naively. So that's the case in toric code. But I want to impose the Gauss law strictly. That means that I need to make this gauge invariant. And the way to make it gauge invariant is that at the end of the site, I put a Z operator. So now this commutes with the Gauss law, but it doesn't commute with the Hamiltonian. It still creates an excitation in the Hamiltonian, but it is gauge invariant. And my claim is that if I conjugate my Hamiltonian by this operator, it will give me another Hamiltonian where a single E anyon is trapped at site R0. So it creates a E anyon that is stationary, static E anyon. And then, as I said, the Z operator is needed to impose the gauge invariance. Now, what does the Hamiltonian look like? Actually, if you conjugate the Hamiltonian, it commutes with everything almost except X operators, calligraphic X operators at site R0, and it gives you this term. So remember that there is a minus X here. So minus X cancels the plus X coming from here, and the phase factor came because I conjugated by the Z here. So this is the new Hamiltonian I have, and then I label it as HE because actually this has twofold degenerate ground state that is associated with the E anyon sitting at the site R0. And now also UT doesn't commute with the naive UT doesn't commute with HE because it also doesn't commute with this unitary operator. I also need to create a new time reversal that is conjugated by this unitary. And this new time reversal turns out to be the old time reversal times Z square, if you do this calculation carefully. But now this operator, it is globally, it's well defined. It commutes with the Hamiltonian with a single E anyon. But now if you take the square of it, because UT also doesn't commute with the Z square, remember that UT has product of X, it squares to -1. So once I trap a single E anyon at some site, my global time reversal operator gets, it squares to -1. It's a projective representation of time reversal. So a single E anyon traps a fractional charge I because U operator squares to -1. And it carries a Kramer's degeneracy. That's why there was a twofold degeneracy. So that proves the claim. So this time reversal operator is interesting because it fractionalizes on the E anyons. Okay. Now I want to look at some boundaries, essentially what Burak asked about with this theory. Since my bulk topological order is just toric code, I'll have two kind of gapped boundary conditions. One will be M condensed. Now I haven't done this before, but in this talk, but what we call M boundary condition is what is known as the smooth boundary condition, where you have the square lattice and you terminate it smoothly. There is no dangling links at the end. And what that really means is that you need to modify your Gauss laws. Your Gauss law was the star and the X square, but now at the end you don't have this dangling link. So you have this new Gauss law that is only acting on the boundary. In the bulk, it's still the old one. At the boundary, it is the smooth star term that is that multiplies the X square. And then the smooth star term only consists of 3 sigma x's. And with this boundary condition, now remember that I mentioned that U square operator, U operator doesn't square to identity. It is only in the constraint Hilbert space. Actually, with this boundary condition, the time reversal symmetry still squares to identity. One can do this computation. So U square is just some X squares, and every X square can be replaced by the star operators, and the product of all stars still vanish with this boundary condition. So it is still identity. What I'm trying to say is that when I have this boundary, at this boundary, my global symmetry, enriching Z2 symmetry, still acts like a Z2 symmetry. And then remember that choosing M condensed boundary means that the E lines become like a Z2 symmetry for the physical boundary. So this boundary condition encodes a Z2 times Z2 symmetry with mixed anomaly. Why mixed anomaly? Because my symmetries are implemented by this U operator and my E lines. But the E lines carry fractional charges under the time reversal. So that's one way of understanding the meaning of mixed anomaly for the boundary theory. So I'm not showing it, I'm just claiming without any proof, but essentially the fact that E anyons carry fractional charge means that for the one lower dimensional theory, this Z2 times Z2 symmetry is actually anomalous. There's a mixed anomaly. We will see a little bit more consequence of that. Now, let's choose the other boundary condition and let's see what happens. So now I look at the E-condensed boundary, and E-condensed boundary condition is realized on the lattice by what's called a rough boundary. Rough boundary means that you terminate your square lattice with dangling links at the end. So the last sides have these dangling links coming out of them. And the star operators are still well defined because they can exist at the boundary, but the plaquette terms needs to be modified. In particular, plaquettes are now at the boundary consist of 3 links. And if you put 3 sigma z operators, they are not gauge invariant because there's some Gauss law coming from here. So you need to make things gauge invariant, so you put a z. So this is the modified rough boundary plaquette operator. That's gauge invariant. But now something interesting happens actually. Choosing the rough boundary leads to an additional twofold degeneracy without even specifying what happens in the other boundary. I mean, this can be some infinite plane, semi-infinite plane. And all I'm saying is that already at the boundary, there's a twofold degeneracy. Why? Because if I take this plaquette term and square it, all the sigma z's are gone, but these calligraphic z's become z square. They become effectively Ising terms. And then they just, at the end, the boundary has this additional term in the Hamiltonian that goes like z square in the ground state subspace. And then that spontaneously breaks some symmetry. In principle, in this case, time reversal symmetry. Because then in the ground state subspace, z square is plus or minus 1 at the boundary. So the time reversal symmetry is broken at the E-condensed boundary. That's very important. Not only time reversal symmetry is broken, so this is not a symmetric boundary because of this is not a coincidence because E anyons were carrying fractional charge, and if I try to condense something with fractional charge, I'm breaking the symmetry. Not only that, but if you look at the square of the time reversal operator, now because of the dangling links, actually it doesn't become identity everywhere. Instead, product of all the star operators gives you this boundary symmetry. That's a Z2 symmetry. So at the boundary, time reversal becomes exactly a Z4 time reversal symmetry. So the E-condensed boundary realizes the Z4 time reversal symmetry. And this is not a coincidence either because M-condensed boundary realizes the Z2 times Z2. Changing M and E implements a gauging of Z2 symmetry. And then I already showed you that gauging that Z2 gives you a Z4 symmetry. And then that's what we are seeing at the level of topological order. And this Z4 time reversal symmetry is spontaneously broken in addition to being extended. Because time reversal part is broken. Actually, this still commutes with the Z square terms. Okay. Now I'm trying to summarize the point of this time reversal enriched topological order. Now I have this enrichment. Notice that this Z2 time reversal enrichment was not permuting anyons. This is a different kind. First, I showed the translation enrichment where anyons were permuted. And then there were Lagrangian algebras that are just not invariant. They were mapped to each other. In this case, there is no anyon permutation, but there is non-trivial symmetry fractionalization, which causes some E-condensed boundary to break the symmetry. So I want to remove the E-condensed boundary. I only allow M-condensed boundary because M-condensed boundary is the only Z2 symmetric boundary. But then if I try to construct a sandwich, I have only one Lagrangian algebra. The only gapped phase of matter can only have M on the both sides because that's the only time reversal symmetric sandwich. And this sandwich gives me twofold degeneracy because there's an M tunneling event. That means that actually, if you also recall that the M condensation chooses Z2 times Z2 symmetry with mixed anomaly, once I impose the time reversal symmetry, I have to break the additional Z2 symmetry. So that's the meaning of mixed anomaly. The only gapped phase with time reversal invariance has to break the other unitary Z2 symmetry. So that's how we detect, or what's the signature of the mixed anomaly in the 1 plus 1D of this in the SymTFT construction. Okay, so with these two lengthy examples, I'm towards the end of my talk. I just want to give some general remarks. So these two are the simplest example in the overarching idea. So you can generalize this idea. More generally, given some 2 plus 1D topological order, if you enrich by a non-anomalous symmetry, that's important. That's the case that we consider, that I label by Q. There are two data that comes into the play, and we had seen simple examples of that. First, there's an action on anyons, rho. This rho is some sort of automorphism that can permute the anyons. But more generally, actually, there's an asterisk here. It can act even more than that. So it may not permute the anyons, but it can have a non-trivial action on the junctions of anyons. So the possibilities are a little more than just permutation. The second data is the symmetry fractionalization. So the symmetry fractionalization class is related to another cohomology group, second cohomology group, where you have the group elements weighted by the abelian anyons, and the rho here signifies potential action. So it's a somewhat complicated object. In the case of time reversal, it was very simple because this was just Z2, this was just Z2, and then the result was Z2 time reversal, and then the result was Z2. So my simple examples for 1 and 2 were the translation case and the time reversal case. Then our proposal is that you can use this construction, symmetry-enriched SymTFT, to classify gapped phases with for which there's a non-trivial interplay of space-time symmetry and internal symmetry. But the rule is that you only consider sandwiches that are that consist of boundary conditions that are Q-symmetric. If you try to relax this condition, either some boundaries are not invariant, or sometimes symmetry gets extended, so you don't get exactly the bulk enrichment that you were looking for or you started initially. So this is probably the most restrictive, but it gives you some reliable information about the gapped phases. So we demand that any such SymTFT must have boundary conditions that are Q-symmetric. What does Q-symmetric means? It means that the Lagrangian algebras are invariant under the action. So little q is an element of capital Q. And then the anyons in the Lagrangian algebra carries no fractional charge. So we don't want any fractionalization. Actually, it turns out that you can show that whenever this is non-trivial, whenever there is some symmetry fractionalization, any such sandwich construction with Q-symmetric Lagrangian algebras describes some anomalous symmetry. So actually, those sandwiches only describe anomalous symmetry. The non-anomalous ones break the symmetry at the boundaries, as we had seen for the time reverse. Then this construction more generally allows us to classify phases with modulated symmetries. So there's an example in the paper, is a bit lengthy. So there's an example in the paper where we classify, for instance, SPT phases with modulated symmetries. You can do it by really having some modulated symmetry and translation enrichment and demanding that there's translation invariant unique ground states and looking at all the Lagrangian algebras that give it to you. And that gives you a classification. And we can use this kind of construction to detect the anomalies of space-time symmetries that is mixed with internal symmetries, not just the space-time symmetry. Okay, with those concluding remarks, thanks a lot for bearing with me, staying here for the end, 20 minutes past the time.
Hocam, thank you for your great talk. Actually, if there are questions, you can ask, or maybe we can stop record and you can ask later after the report.
I have one question. So first of all, thanks for the great talk. If I understand correctly, what you're trying to do is like to get some SymTFT for space-time symmetries, you're using mixed anomalies with internal symmetries, right? So when we consider four-dimensional SU and gauge theory, at theta equals pi, there is a mixed anomaly between the center symmetry and the time reversal symmetry. Can we apply this construction to that?
Yeah, definitely. We did the 1 plus 1D. because the Lagrangian algebras are more under control and everything.
Mhm.
But actually, there's an issue because if you want to keep the full SUN symmetry, I'm not very familiar about how to do the SymTFT with continuous symmetries either. But I'm guessing that probably the anomaly is between some discrete subgroup. Then I can take the SymTFT of this discrete subgroup and time reversal. And yeah. And yeah, I can just apply. I think 4 plus 1D. So you need 5 plus 1D topological field theories. I don't know.
Sorry, I meant 3 plus 1D gauge theory, not 4 plus 1.
Okay. So you need 4 plus 1D. My answer doesn't change actually. I don't know a lot about 4 plus 1D topological field theories, but I think the general characterization is, I mean, okay, this data is clearly for 1D, but the idea can be easily generalized. It should hold because it's just the idea of enriching the topological field theories with some global symmetry.
Thanks again.
Also,
for the talk.
I have a question, hocam. I'm not that good in the SymTFT, so I'm just asking this a question to figure out what is its limitations. So we just consider the toric code as an example, and the simplest example for the LSM, LMS anomalies by Z2 cross Z2. But can we consider again this sandwich construction with, for example, a fractional quantum Hall effect, maybe? Because again, there is engines, there is again symmetry fractionalization, but you talked about discrete gauging, right, at the beginning.
Even before that, there is an issue. In this SymTFT construction, we always think of topological field theories with at least one gapped boundary. With fractional quantum Hall, you don't have any gap boundaries because boundaries are chiral. So actually, that's a question that people ask frequently. I don't have an answer. I don't know if such a quantum Hall state, fractional quantum Hall state, would correspond to some symmetry. But at least so you see it's a mathematical trick. So I want to describe the symmetry of the D-dimensional theory by a D plus 1D theory, and I want to have at least one gap boundary. That's why I'm not thinking about the chiral theories. So that's one reason to not look at the fractional quantum.
Oh, okay, thank you. I just missed that.
It's
nuance when you
I
talked
didn't say it. So by construction, we always assume that the bulk topological order or topological field theory at least has one gap boundary. So we are only restricting ourselves to those cases. Yeah.
Okay, thank you. If there are no other questions, we can stop recording, by the way.